This is the Solid Signal podcast for the week of March 13th, 2023. And the week after the Oscars airs, I usually do some sort of podcast about how the Academy got it wrong and how this is the death of movies and blah, blah, blah. And I think I've done that pretty much every year for the last 10 years. I am not doing that this week because I actually think the Oscars got it right last night. I don't want to spoil it for you, but I guess it's been at least 24 hours, so you probably read it in the news that Everything Everywhere All at Once won pretty much every award everywhere all at once. And I think it deserved it because here's a film with very similar content to something like Doctor Strange in the Multiverse of Madness, and it was made on a tenth of the budget, and it's 10 times better, at least in my personal opinion. So, putting all of that aside, let's talk a little bit more on topic this week, and the subject is polarization. And I'm not talking about the polarization of different people politically, because when we talk about polarization and being a polarized community, that ends up being what happens. But I'm talking about antenna signal polarization and why this is something important, something that you do need to know. Now, I'll admit that if I were doing a video on this, it would be a little bit easier to illustrate. I'd have to do some snazzy CGI to show you, but instead I'm going to ask you to employ your imagination and try to follow along where I'm going. I'll try to be as descriptive as I possibly can be. When it comes to TV broadcasting, and in fact all forms of broadcasting, there are a lot of different characteristics that define the signal that you're going to get. Is it analog or digital? That's a big one. What frequency is it on? Because we've got this entire big thing called the electromagnetic spectrum, which comprises visible light and X-rays and radio and TV broadcasts and just about everything else that gets us from point A to point B. And you can use different chunks of it to do different things. If we couldn't, well, there would only be one broadcast possible at a time, and that would be it. And broadcast power comes into play, the technology used, whether it's amplitude modulation, frequency modulation, or quadrature amplitude modulation, which is practically impossible for normal humans to understand. However, that's all being done. These are different ways that we characterize signals, and I'm not going to talk too much about those this week. I might in future podcasts, so hang on if you like this kind of technical stuff. Just keep listening. No, this time I'm talking about polarization. And why? Because a lot of times the question comes up, what is going to happen here? What is going to happen there? And the answer is almost always that polarization solves the problem. First, let's define the terms. You got to kind of think of broadcasting in terms of a wave. I mean, literally, you've seen that kind of sine wave thing, where it just goes up and down and up and down. You've got to have seen it at some point in your life. And it doesn't really go out in three dimensions most of the time. Most of the time, you're going to have this wave. It's either going to go up and down as if you were drawing this sine wave on a wall, or left and right, left and right, left and right, as if you were drawing it on a table. When it goes left and right, we call that horizontal polarization. And when it goes up and down, we call that vertical polarization. Why the two different kinds? Well, it has to do to some extent with tradition. It has to do with some extent with how you want the signal to be received and how you're going to put up the antenna. And also, it doesn't necessarily mean that one antenna won't pick something up, but it's just kind of the way that it does it. So, TV signals in the United States are horizontally polarized. They're horizontally polarized because here in the U.S. especially, we have been using the VHF band ever since the very beginning. And for VHF, you need a very large antenna. You need an antenna that is a good 6 to 9 feet wide in order to get all the signals that you want to get. Now, so the antenna has to be put at the same orientation as the wave. So if your wave goes left to right, left to right, left to right, your antenna comes out left and right. And if you think about those big old antennas on roofs, that's what they look like. They're just a bunch of sticks going out left and right parallel to the horizon. If you had a vertically polarized TV signal, well, then the antenna would have to be sideways, meaning those sticks would go up and down, and you'd have to put the antenna much, much higher, or else the antenna itself would bump into the ground or into the roof or whatever it is you're putting it on. So horizontal polarization makes a little bit more sense there. Other countries really just started with UHF broadcasting from the get-go, and some of them have decided to use vertical polarization because the size of the waves just doesn't make as much of a difference. For cell signals, it makes even less of a difference because the wavelength of cell signals is much smaller. Backing up for just a second, as you increase the frequency, the waves get smaller and smaller and smaller. So for a relatively low frequency thing like TV broadcasting, you get really big waves. For a relatively high frequency thing like cell phones, you get really, really small waves. But at least in the United States anyway, the cell signals are vertically polarized, which makes it so that your average cellular antenna goes up and down, not left and right. But it makes less of a difference than it does with TV broadcasting. And again, it has to do with the size of the waves. When you have an antenna that's pointing the wrong way, if it's not completely level or straight up and down plumb, then you're not getting all of the signal. You're only getting the part of the signal that intersects that piece of metal as it sits. And that's really important when your wave is like 6.5, 7 feet long. But as you get to the point where your waves are, 1 inch, 2 inches in size, really you see a lot less of that being an issue, which is why, by the way, you do not have to hold your cell phone at any particular angle in order to get reception. Horizontal polarization and vertical polarization can work together, and they don't bother each other for the most part. This is kind of an interesting, neat thing about it, that you can have, for example, a horizontally polarized signal that goes left, right, and you can have a vertically polarized signal that goes up, down, and if they're just a tiny little bit out of phase, you can kind of imagine how one signal could almost fit in the space made by the other signal. This means you can use the same broadcast frequency twice. And this is one of the proposals for the next generation of television broadcasting, which is putting data services on the vertical polarization while regular TV services are on the horizontal polarization. This would allow for a lot more information to come to the house with the same frequencies. And remember, frequencies are not an infinite resource. There's only a certain number of them, so the more you want to put on there, you either have to use more compression to try to figure out how you fit that, or you use tricks like changing the polarization. Now, at this point, we've talked about horizontal and vertical polarization, and those are pretty easy to understand. On the other hand, there's circular polarization, which is a lot harder to understand because what happens is that the signal kind of travels through the air like a corkscrew. It's going in a big circle instead of left, right, or up, down. It's going both left and up, right and down at the same time. Now you can imagine it's harder to make a circularly polarized signal, so you're only going to do it if you're a broadcaster, if there's some benefit to it. And there are two cases to really think about where circular polarization actually helps you out. First of all, at least in the United States and North America, as it were, FM broadcasts are circularly polarized, which is actually something I learned when I was researching this podcast. I had thought they were horizontally polarized like TV signals, but guess what? They are not. When you have a signal that is circularly polarized, you can get it by tilting the antenna at any orientation. So an antenna that goes left and right is going to pick up FM signals great. An antenna that goes up and down is going to pick up FM signals great. And if you think about it, that's actually kind of what you want, because it got like a car where the FM antenna goes up and down, and then you've got, a land-based FM antenna, which can be something mounted on the roof, or sometimes it can just be a wire hanging out the back of whatever it is you want to use to receive. And it could be pointing in any direction. And so circular polarization means that you get better reception no matter how the antenna works. You would think something like this would be needed for cell signals, but it's not. As I said, cell phone signals, the waves themselves are much smaller, so the amount of signal you get with an antenna pointing in any particular direction is going to be roughly the same, and so it's not as important to hold the phone in any particular way in order to get service. Speaking of cell phones, I wanted to, before I go further into circular polarization in the other case, I wanted to bring up that because cell phone signals are vertically polarized and TV signals are horizontally polarized, there is less interference even in the bands where they could potentially interfere. If you have an older TV antenna, anything older than 2 or 3 years old, it's tuned to get signals that are now used for cell phones, but you don't really need to worry about it so much because that antenna is going to be tuned to receive horizontally polarized signals, not vertically polarized signals. Getting back to circular polarization for a second, the other use case where you would use circular polarization is in satellite television. Why? Because oftentimes in the United States, you have more than one satellite, which is why you have a dish with like multiple little white feed horns on the front of it, because it's trying to receive signals from more than one satellite at the same time. In order to do that, you have to tilt the antenna a particular way so that all the satellites are lined up parallel to the feed horns that are receiving them. However, if you do that, and if you had horizontal polarization, well, you wouldn't be receiving signals very well. Now, satellite frequencies are really, really high, and so the waves are really, really small. And so you would think, like cell phone signals, that it really wouldn't matter what the orientation of the antenna would be. But also remember that they are incredibly, incredibly weak. They come from 20,000 miles away, and they aren't that strong to begin with. So you need every possible advantage to get reception from a satellite antenna. That's why circular polarization is used. And just like you can have horizontal polarization and vertical polarization, they don't interfere with each other, you can also have what's called left-hand circular polarization and right-hand circular polarization, which if you do this with your finger, I'm doing this with my finger and you can't see it because I'm recording a podcast. If you make that corkscrew motion clockwise, well, that's right-hand circular polarization. If you make that corkscrew motion anti-clockwise or counterclockwise, that's left-hand circular polarization. And this is used in satellite broadcasts to make sure that you can get as much as possible out of the few frequencies that you have. Remember, you're sending about 2 terabytes a second of digital data down from the sky, and you have a relatively small number of frequencies to do it with. So using them smartly by using both kinds of polarization actually makes an awful lot of sense. You know, there's a lot more that can be talked about when we talk about polarization, and there's, how we would mount the antennas, how we would design it, and how you could even create a transmitter that even does this in the first place, which is pretty amazing that they can think about that, especially since you can't see these waves and you have to wonder, how do you know if they work? But the science of broadcasting is pretty advanced at this point. It's been around for about, 150 some years. So they've obviously figured out all this stuff. So when it comes to polarization, the most important thing that you, the user, need to know is that depending on your antenna, you may need to point it a particular way. If your TV antenna is one of those kind of square panel-y looking ones, like the Televez Evoca, you don't have to worry too much about how you point it. But if it's one of the more Yagi type of antennas, like the HD 8200 XL that we have at Solid Signal, you're going to have to make sure that it's pretty parallel to the horizon in order to get the best possible results. And results are really what you're shooting for. You don't buy these things for their entertainment value purely by themselves. So that's about it for this technically dense Solid Signal podcast. For those who are looking for a little bit more of a dose of entertainment and crankiness, I'm sure it will be back again in the coming weeks. But in the meantime, shop at solidsignal.com, the sponsor of this podcast. They are the ones who pay my paycheck and sponsor and give me all the equipment to do all this stuff. So if you like what you're hearing, go ahead and shop over at solidsignal.com. because you will find the best selection and the best prices. If you have any questions, call them at 888-233-7563. In the meantime, do me a favor, like and subscribe, makes me look good to my bosses, and I will see you again next week on the Solid Signal Podcast.